All right, let's dive right in. We're going to pull back the curtain on graphs, the hidden blueprint behind pretty much every network you can think of, from your own social circle all the way up to the internet itself.
So what do all these things really have in common? Well, they all share the exact same fundamental structure. It's a really powerful idea from math, and here's the cool part. Once you see it, you start seeing it absolutely everywhere. Stick with me, and I promise by the end of this, you'll see it too.
Okay, so first things first, what is a graph really? Let's get past the formal textbook definition and see how this abstract idea connects directly to the world all around us. Now, formally, you'll see this written as G equals VE. Don't let that intimidate you. All it means is that a graph has two parts. First, you've got V, which is just a set of vertices. You can think of them as dots or what we often call nodes. And second, you've got E, which is a set of edges. Those are just the lines or the connections between the dots. That's it. Simple, right? But believe me, this incredibly simple idea is the foundation for everything.
And once you know what to look for, you'll realize these things are everywhere. Your friendships on social media? That's a graph. You and your friends are the nodes, and the friendship itself is the edge. Roads connecting cities, hyperlinks connecting websites, even the dependencies between tasks in a project plan, yep, those can all be modeled as graphs.
But here's where it gets interesting. Not all connections are created equal, are they? So let's talk about the three main variations or flavors of graphs. You're definitely going to want to know these.
First up, we have undirected graphs. The easiest way to think about these is like a two-way street. If you've got an edge between point A and point B, the connection is mutual. It goes both ways. A friendship on Facebook is a perfect example, right? If you're friends with someone, they are automatically friends back with you.
So if we have two-way streets, it only makes sense that we also have one-way streets. These are called directed graphs, or digraphs for short. Here, the connection has a specific direction, usually shown with an arrow. An edge goes from A to B, but, and this is key, it does not automatically mean there's a connection going from B back to A. Think about following someone on Twitter or Instagram. You can follow them, but they don't necessarily have to follow you back. That's a directed connection.
And for our final flavor, we add another layer of really useful information with weighted graphs. In this case, every single edge has a number attached to it, a weight. And this weight can represent just about anything you want. It could be the distance in miles between two cities, the time it takes to fly between two airports, or maybe the cost of sending data over a network cable. This adds a crucial dimension of cost or effort to our network.
So, we've got these cool abstract ideas, but how do we actually represent them inside a computer's memory? Now, this isn't just an academic question. The choice you make here has huge implications for performance, especially depending on how many connections your graph ends up having.
It turns out there are two classic ways to do this that every computer science student learns: the adjacency list and the adjacency matrix. So let's break down the pros and cons of each.
All right, this table really lays out the core trade-offs, so let's spend a second here. First, let's talk about space. An adjacency list is super efficient. It only stores the connections that actually exist. But an adjacency matrix, well, it creates this giant grid for every possible connection, whether it's there or not. That theta of v squared notation is just a fancy way of saying its memory usage explodes as you add more nodes. So why on earth would you ever use a matrix? It's all about that trade-off. It can tell you if two nodes are connected in what we call O of 1, or constant time, which means it's basically instant. The list can be a lot slower for that one specific question.
So here's the bottom line. Your choice really depends on the graph's density. For what we call sparse graphs, where nodes have just a few connections, like a social network, an adjacency list is almost always the better choice. It saves a massive amount of space. But for dense graphs, where almost every node is connected to every other one, an adjacency matrix can actually be a pretty good choice, especially if you need to constantly check if an edge exists between two nodes.
Okay, so we've covered the theory, the different types, and how to store them, but so what? Why should you care? Well, now we get to the payoff. Let's see how all this knowledge helps us solve real, tangible problems.
This is where it all comes together. By modeling problems as graphs, we unlock this entire toolbox of powerful algorithms. Finding the fastest route on Google Maps? That's just a shortest path problem on a weighted graph, solved with an algorithm like Dijkstra's. Need to figure out the right order to take your college classes based on prerequisites? That's a topological sort on a directed graph. All of a sudden, these really complex problems become totally solvable.
And hey, if you're ever in a technical interview, This right here is pure gold. Don't just pick a representation out of thin air. Justify it. Saying something like, I'd use an adjacency list here because the graph is likely sparse, that one sentence shows you understand the fundamental trade-offs. It demonstrates a much deeper level of thinking, and that's exactly what interviewers are looking for.
And here's another little pro tip that can make all the difference. A lot of these famous algorithms have some fine print, They come with conditions. Dijkstra's algorithm, for instance, is amazing for finding shortest paths, but it completely falls apart if any of your edge weights are negative. It just won't work. Knowing these little constraints is a sign of a really seasoned programmer.
So there you have it. We peeled back the curtain on the hidden structure of networks. You now have this new mental model, this new lens to see the world in terms of nodes and edges, of directed paths and weighted costs. So the question is, as you go about your day tomorrow, what invisible networks are you suddenly going to be able to see?